the research we're working on, thermal performance. That's the big thing right now. So showing that brick wall systems perform as well or better than other wall systems. That's a big thing I've been involved in. I'm not a civil engineer, but we're doing civil engineering work right now. And when you look at numbers, for example, for that type of work, you look at what other building materials are saying. They claim a certain R value. Okay, R value is only based on an artificial measurement where there's no temperature change. Well, we live in a real world where the temperature cycles from day to night. Bricks store heat, and they prevent that heat from going into the house. I grew up in Charleston, South Carolina, so I always think of a hot climate. But when you talk to guys in a room like this from Ohio, they're worried about the opposite. So in the winter, the heat leaking to the outside. But since the bricks store the heat, they actually perform a lot better than that R value number tells you. But it's very hard to measure, and so that's what we're working on. And we're putting together, I'll be talking later this week at our research meeting about how we compare to other wall systems. And even just on an R value basis, when you do a fair apples to apples measurement, we're 14-15% better than vinyl siding. We're better than hardy board. Okay, just in that artificially simple type of measurement. When you go to dynamic measurements, depending on how extreme the temperature is, we can be 50% better from an energy point of view. So there's some huge advantages from brick construction that we're trying to put on paper that salespeople can use to sell more brick. When they sell more, you make more. All right. So we all benefit. That's what we're trying to do. So that's what we do. Mike manages the ASTM testing and a lot of the services we do. If you ever a customer needs a certified report, we have certifications from ISO and another group in the U.S. called AASHTO to do the brick property test. And he'll be talking to you some about brick properties a little later today. So I'm going to start at the most fundamental point, raw material. And I'm just going to give you an idea of what we're looking for in raw materials. Now, we're unique, I think, in our industry in that we don't use refined materials. Everybody else is doing a lot of processing, for the most part, on their material to get it in the form so they can make a consistent product. We're taking stuff out of the ground, we're not doing a lot of processing, and we're trying to make a consistent product. So we have a unique challenge. Another thing is every raw material is different. And because of that, we have to really keep an eye on what we have and how it's changing to be able to make a consistent product. So, Jim, you got the first one ready?
Oh, hang on.
All right.
Just a second. I should be ready, but I'm not.
A little while on drying. Drying can be pretty dry, pretty not exciting. How about that? In the old days, we used to bring out the psychrometric charts, and we used to do all kinds of calculations. You can still do that, but there are a lot of free apps now that you can get that will get you all the psychrometric properties, and I'll explain what I mean by that, instead of having to read the charts, and it makes things a whole lot easier. So we'll talk a little bit about that. But the main thing is we go through this, I want you to understand there are resources on our website. So we've done webinars on these topics. Each of these is basically one of those webinars. So if there's something that maybe I go too fast, and at any point you can interrupt me. You won't hurt my feelings. I'd rather answer your question than leave you wondering. But you can go back, you can watch these on our website. All of you have access to that because you're members of the center because of Acme Brick. There's also a really neat resource that had some malicious activity a couple of weeks ago, so we're still working on it, trying to get it back up. But if any of you have ever met Don Dennison, he did a lot of work putting together Wiki Brick. And there are answers to really common manufacturing questions in it. And it's open, you can post replies, or you can add your experience to it if you want, but it's a really good, I'm seeing, this scumming. What do I do about scumming, just for example? And there's a lot of practical information in there on what you can do. It's like a resource we don't use very often. But as soon as we can get it cleaned up and back online, it will be a good resource. So WikiBrick, You get to it through our website, which is brickandtile.org. So when we look at raw material, we typically break it down into 3 sizes. Anybody ever done a particle size analysis? Yeah. Where you break down the raw material? If you've been to the short course, we do that there. And we break it down into 3 sizes, and we'll talk about this as we go through. Each of these sizes is important. The first one's a little unfortunate because we call all of the coarse particles sand. And sand, you think of it's all silica, but it's not necessarily silica. It's the coarse particles. And typically they're going to help us control shrinkage and control size. Now, I believe here when you do particle size, you make a break for silt at 20 microns? Yeah. Okay. Some people do that. They do that. That's common in Germany too. We happen to use 74 micron, that should say micrometers, or a 200 mesh screen. So anything that goes through a 200 mesh. If you've done particle size, 200 mesh looks like a piece of cloth. You can't really see the individual openings. It's pretty small. And then anything that's less than 2 microns we call clay. Now there are times, raw materials we've seen, where you get a good number for this, but it's not really clay, it's fine sand or something like that. It just happens to be in the size. Those names are strictly to do with particle size. So when you're measuring particle size, the question that always comes up, well, what should I get? Well, what you should get is something consistent that you know how to work with. You don't want to see big variations. A rule of thumb, Jim Frederick, who used to do this with me, he was here last time. I did this probably 10 years ago, I think. It's you want to be roughly a third of each of your particles. How often do I see that when we're doing particle size? Not very often, okay? But that's just kind of a rule of thumb we're looking for. Now, the other thing to think about is if you look at this guy, we would call this agglomeration. So these little clay particles, and this is important for a lot of things. That's part of where plasticity comes from in the material. The little particles have surface charge, and they like to stick to each other, and they like to stick to the bigger particles. Okay, so when they're doing that, they're not necessarily giving you all the benefit you would expect for each of the size. So the clay size fraction is primarily what's responsible for the green strength we're looking for. Okay, and there are things you can do through mixing, water addition, deflocculants to help break up those agglomerates. But that's something always to keep in mind when you look at the raw material. They do like to ball up on us. And then this is another shot. The other thing to consider is these things are actually little plates. Okay? When you do a sedimentation analysis, for those of you who've done it, or particle size analysis, that's all based on the assumption that you're dealing with little spheres. Okay? So there is no such thing as a true particle size distribution. They all have assumptions. And we've got a technique now called laser scattering. So if you've done the sedimentation, you know it takes 2 days basically to get a result. It's kind of tedious. You don't get a lot of data points. The laser scattering can do the fine fraction in under 2 minutes. But they agree down almost to that point where you make the clay break, and then they diverge a little bit. And it's because of that assumption of particle size. So the sedimentation assumes you've got a sphere settling at a certain rate. Well, you really have a plate. Okay, so it doesn't settle at the rate you're expecting it to. In the laser scattering, sometimes you've got a particle lined up like this for the laser, okay, and it's scattering off that. Sometimes it's sitting on edge and it scatters differently. So you get different results based on particle shape. So that's something we're working on right now to be able to do faster particle size analysis. If we can do it faster, it just costs less, and we can develop more information. You still have to break out the coarse fraction for both, for different reasons for both tests, but it's a 2-stage process. So when it comes down to it, what is absolutely necessary, and this comes from a very old dictionary of ceramics that was published probably in the 20s or 30s. What do we need? Well, we need enough plasticity to hold the thing together, okay? What is plasticity? What is cohesion? So if I take a lump of clay and a wet lump of clay, and I squeeze it and let go, and it keeps the shape of my hand when I squeezed it, that's called plastic deformation. If I took a rubber ball and I squeezed it and let go, it returns to its original shape, that's elastic deformation. Okay, so plasticity means the ability to deform and hold its shape. So we need a material that's got enough plasticity that it's going to be able to hold together and have enough green strength or cohesion that we can handle it. So you can pick it up, you can put it on a car, you can put load on top of it, and it doesn't deform as a result of that load. Okay, so you think about it, the brick on the bottom of the car has a lot of weight on it. Okay, the green brick as it's going into the kiln. And then the other thing is it's got to vitrify. Vitrification is an old-fashioned word that means making glass. We talk about firing it in traditional ceramics as vitrification sometimes. Okay, we're making a glassy glue that holds everything together. And so what we're looking for is a material that has a sufficiently wide firing range that we can accommodate the temperature variation we know happens from the inside to the outside of the car without turning anything into a puddle. Okay, and there are materials that just in a few degrees they'll go from being a solid to a liquid. That doesn't work because we don't have that kind of control on a big kill car. So we need something that's got a wide range and is very tolerant of temperature deviation to give us the process we're looking for. And that's mostly a result of the chemistry. Okay, so there's the particle size influences the plasticity of the material and its shrinkage and its green strength and all that kind of stuff, whereas the chemistry has to do with what happens in the kiln, how it fires, how much glass you make is a function of temperature and time. The other thing that makes ceramics a little harder than dealing with other materials, if I deal with a metal, okay, I can look at a chart, and if I want to convert iron into one of its different forms, and I don't know the chart, so I'm not going to throw out names, I can see a certain temperature, and I go to that temperature and I let it sit, and that reaction takes place. So they're generally pretty quick. In clays, everything is a lot more sluggish. We call it kinetic control. So it's a function of temperature and of time. So say I want to I'm firing to 2000 F and I've got a 5-hour soak, and I want to drop my absorption a couple of percent. Okay, I can either go to a higher temperature or I can hold for a longer time. Usually temperature is more effective of the two, but leaving it for a longer time could do the same thing. So temperature and time influence everything. So the chemistry influences the range, firing temperature range. Another way to say that would be the range over where we form glass, and how viscous that glass is, because that influences whether it's going to be a puddle or it's going to hold together in a brick shape. Obviously fired color, we'll talk more about that later. Generally though, we're looking at the iron oxide content. And iron can do a lot of things depending on how much is there and the kiln atmosphere. Okay, you can change that iron a lot to give you a lot of different colors. That's what you do when you flash. I'll talk a little bit about emissions tomorrow. So the extra stuff that's in there can lead to emissions. And then sometimes the the accessory minerals, the extra stuff that's in there, can give us scumming. That's salt deposit in the dryer, or efflorescence. That's salt deposits after it comes out of the kiln. Usually they're coming from the same thing, but it's just where it occurs. We give it different names. The chemical makeup of the material can lead to that. And we'll talk a little bit about how you look for these things. As far as the functionality or the contribution of particle size, so they're both important. Plasticity for extrusion, obviously. The way the material flows through the extruder, we call that rheology. I've been talking about that a little bit lately in the webinar. We've got a new tool for measuring that. The way the particles pack together. So the particle size distribution affects the density and the properties. So if I can get the material or the materials to pack together better in extrusion, I may see less shrinkage, I may see a lower water absorption. And typically you can do this kind of thing with one of the easy ways with a lot of materials, add a little bit of soda ash. But the problem is you get a tighter body, it's also harder to dry, okay, because there is not as much channel for the water to get out. So Dr. Robinson, who started all this, he used to say what helps you somewhere bites you on the butt somewhere else, okay? And that's really true with ceramics, okay? When we're dealing with these things, you may make an improvement somewhere, but it may have a cost somewhere else in the process. And then the drying characteristics and the shrinkage. So we'll talk about that more when we get to drying a little later on. So just some chemical analysis to throw out. This is for a number of materials. So this would be like a clay, maybe Alabama or Mississippi type clay. Fire clays, probably out of Ohio. I think the shale's out of Ohio. And these two were Texas materials, if I'm not mistaken. But there's not a whole lot of change. Now, the one thing you have to understand when you do a chemical analysis, now this is telling you it's good to do particle size. Particle size tells you if there's going to be any big changes in the way the material flows through the extruder, shrinkage changes, things like that. Usually if there's change in the particle size, there's going to be a change in chemistry too. And that's where things start to change in the kiln. But when we do a chemical analysis, we are really just measuring like the aluminum, the silicon, the sodium, and by default we're assuming they're oxides. Okay, that's just the convention on how this works. So we're not actually measuring SiO2, and I mention that specifically because that causes a lot of confusion. People see that number and they think, well, I've got 67% quartz. Now, you've got 67% silica somehow distributed in your material. It could be in mica, it could be as part of the clay mineral. Okay, so the silica can exist in a lot of forms. It's not necessarily quartz, and we'll talk about quartz as we go along. But you'll see there's not really, in all these materials from around the country, you know, there's sort of a range that we typically see here on the silica number. This one's probably getting a little bit on the high end, but usually we're seeing that number somewhere in the 60s. And I do a lot of chemical analysis, and it's always surprising how similar these things are. One of the things, that clay fraction usually kind of tracks with this alumina number, okay? The higher that alumina number is, usually the higher the clay mineral, okay? So they tend to be a little more plastic sometimes. Not always the case, but it's a good indicator. If you see a good number here, you know, something in the high 20s, you can expect a reasonably plastic material. This guy right here, I wouldn't expect to be terribly plastic at all, okay? Because it's just what the analysis tells us. These guys in here, especially the sodium and potassium, they're the fluxes, okay? That's what helps lower the firing temperature. The more of those guys you see, usually the lower your firing temperature is going to be. So you can kind of look at this and get an estimate of where the firing temperature is going to be on it. So I kind of, as a rule of thumb, assume everything's 2,000. And depending on how high this number is, I go up or down. Okay, it's not perfect. It's just kind of an art thing that I've picked up over time. But I would expect this material to have the lowest firing temperature of the group because it's got the highest sodium and potassium number. So those are real good indications of what's going to happen in the kiln when you fire the material. To a lesser extent, the magnesium and calcium are also fluxes, but you got to watch this number. A lot of times, we haven't talked about lime pops yet, but we will. That's a good indicator that lime pops may be a problem, okay, because calcium carbonate is what causes lime pops. So if you see a high number there, that's usually an indication. Titania is just naturally occurring in most clays. We don't worry about it. Manganese can be a colorant. Okay, it can influence color. We'll talk more about color later, but that's your main colorant, the iron oxide. So this you would expect to be, you know, probably a buff or tan firing. The reason I say tan is titania tends to push things a little toward the brown. Okay, so if you've got a low iron material but it's got a high titania, you'll get a buff color. It's just the way it works out. And then phosphorus, we don't really worry about. It's just sort of a normal one. And then this loss on ignition. Okay, that's always something we measure on the raw materials. It's basically how much weight the brick's going to lose going through the kiln. Okay, and that can be from a lot of things. Primarily, it has to do with the clay mineral breaking down. So again, that number can be an indication of clay content. So you see the material I said with the highest alumina also had the highest loss on ignition, goes together. Okay, that's probably got a lot of clay mineral. The one I said was probably not very plastic, also has a low loss on ignition, meaning there's probably not a lot of clay mineral. So the clay mineral contributes the most to that number, but it can also be carbon. Okay, pure limestone, if you heat it up, loses 44% of its weight. So it doesn't take a lot of limestone to make this number really big. So that's another thing we kind of watch to see if lime pops may be a problem. It could be organic carbon. It could be sulfur. If you've got pyrite or I used to work for Dilettante for a number of years on the south side of Dallas, and we used an East Texas ball clay that, depending on how they mined it, was loaded with marcasite. Has anybody ever seen marcasite? Okay, it's the same thing as chemically as fool's gold, but it looks like little black tree roots. And it gives you pyrite pops, basically, when you fire the material. So, you can use that number as an indication of those things. You don't have to measure everything directly. Sometimes you can use a number as a flag that tells you, hey, you need to go take a closer look at this material. And that's what we do a lot. So I'm not going to bore you with this, but if we really got into what kaolin, so there are 4 types of clay minerals. Kaolin is sort of the main one we consider because it's in most materials. And you tried to look at what that crystal structure looked like, it would look something like this. So basically you got these blue things, hydroxyls, and when that clay mineral decomposes in the middle of the preheat, you're losing that part of the mineral, and it's no longer clay after you heat it through that point. Okay, you have a relic until you start to get up to the point where you form glass. So if you heated something to, say, 1,000 degrees Fahrenheit, you cooled it off and you tried to re-extrude it, it wouldn't be plastic anymore. Okay, because you've destroyed this mineral that's giving you the plasticity. And they're different types. In parts of East Texas, well, I would say South Texas, more like the plant outside of Houston. Yeah, Sealy. A lot of montmorillonite. Montmorillonite is a different type of clay mineral. Has a little bit different structure than this, but it's extremely high surface area, extremely small particles, and really likes to hold on to water, which makes it difficult to work with. So where does plasticity come from? This picture didn't come through too well, but what it's showing is it looks like a deck of cards if you could see it. Okay, so all the little clay platelets stack up, and they look like a deck of cards. And they do that because the clay minerals have different charges on them. And so you have negative charges on edges, positive charges on the faces of the plates, and they like to stack up with each other to satisfy that charge, just like magnets would. They act like little tiny magnets. And we can modify that surface charge sometimes if we need to. If we have a very high clay content, we might need to use a deflocculant. Like, anybody ever use soda ash? Okay, soda ash is a deflocculant. You're modifying that surface structure, and usually when you add something like that, you get more plasticity with less water, right? You don't have to add as much as before. And that changes the way the material behaves, usually for a good thing. So here are the clay minerals. Kaolin's the most common one, and it can be in anything from the really fine china clays, low iron content, kaolins that you might use to make tile or toilets or something like that. Shales, when you have a little more impurity, or they're also in ball clays you may use in your coatings. And they call them ball clays because they used to go down in pits and they'd ball it up, make a big ball and roll it out of the clay. Because it was plastic enough they could do that. So they'd build up like a snowball and roll it out of the mine. The montmorillonites, okay, those are the materials that really love water, and these can be some of the harder ones to deal with. Places that have a lot of montmorillonite, once the car's dry, you never want to let it sit out in the air on a humid day before it goes in the kiln, because they can pick up water really fast, and they can pick up enough that it causes problems. So the montmorillonites give you great plasticity, but typically are very hard to dry. In the Midwest, you get into things called illites. And illites are basically mica particles that have gotten weathered down fine enough that they're considered clay particles, but they typically don't have a whole lot of plasticity. They're still good, and they fire well. They're easy to work with. You just don't have a lot of plasticity to deal with in them. And then you go out west. There's these minerals called chlorites that don't. Some people say they're not clay minerals. Some people say they are, but you see those on occasion. You would think they have a lot of chlorine because of that name, but really they have a lot of magnesium and iron. They tend to be kind of green color before you fire them, but they make beautiful reds as long as they have enough plasticity to work with. And there are things you can do to improve plasticity. We'll talk about. So these are chemistries of the different clay minerals, and remember I said alumina is usually a good indication, especially if we're talking about kaolin. So you can see a pure kaolin's got a high alumina content. Typically, with the exception of the montmorillonite and the illite, they don't have a lot of fluxes. This is a pure kaolin. I've got to get it up probably 2500 F to get any meaningful vitrification taking place. Okay, so it takes a high temperature, whereas the montmorillonites and the illites are going to fire out at a much lower temperature. And remember I was telling you about the LOI? Okay, most of what I was telling you dealt with kaolinitic materials. But kaolin has a very high LOI, about 15% for pure kaolin. So usually the higher that number is in the raw material, and remember we were looking 6 to 8 in that previous chart, the higher that is, if it's a kaolinitic material, usually the more kaolin there is in it. So we use the LOI as a rough estimate of how much clay mineral. It also can give you information about organic carbon, carbonates like calcium carbonate for lime pops. It could give you information about sulfates we haven't really talked about yet. But they all contribute to that overall LOI. So just because you see a high LOI doesn't mean it's a high carbon or it's got limestone. There are too many things that go into it. It's another easy quality control tool. So you can watch it over time, and if you're seeing changes, then you've got a clay change or you've got an accessory mineral. One of your accessory minerals has changed. So it's a good, easy tool to see if the material's consistent. That SiO2 number, remember if it's a chemical analysis, it's just telling us the total. The way I like to think about it, I grew up loving Legos. So with Legos, they're the pieces in the box. Okay, the chemical analysis tells me what pieces I've got to work with. All right, it doesn't tell me how they're put together. The mineralogy, which we'll look at that in a second, the mineralogy tells me how those pieces are put together. So if you want to think about, if I've got a box of Legos, the chemical analysis is the list of pieces that are in the box. Okay, the instructions are the mineralogy. It tells me how those pieces go together to form the compounds that I'm going to have to deal with. Okay, and how they behave. So if you like Legos, that makes a lot of sense. We like to look at the sodium and potassium because those are the fluxes and give us an idea of where that material is going to fire out. Okay, how much vitrification we can expect. The calcium, magnesium, and iron can also act as a flux, but typically calcium we want to watch out for because it's usually, if we see a decent calcium content, there's a high probability of lime pops. Okay, it's pretty easy to pick those out a lot of times, or those raw materials that are susceptible out. And then iron and manganese give us an idea about fired color. Okay, yes sir.
Where do lime pops go in?
Lime pops, I'm going to talk about it in just a minute. So you obviously don't have a problem in your plant if you don't know what it is. But lime pops we see a lot of those. They go in phases around the country, and we haven't seen it in about 6 or 8 months. But the year before, we had complaints from everywhere dealing with those. I don't know why they seem to be periodic. So just an idea of onset of vitrification and the different amount of fluxes. So if we look at these materials, I use something called a dilettometer to look for the onset of shrinkage in these, or where they start to form glass. I said greater than 2,000, but it's probably a lot more than that. I was being generous here when I made this chart. So this wasn't the purest kaolin. A very pure kaolin, you'd get up very high temperature before you see any meaningful vitrification. Remember, the montmorillonite, the chlorite, and the illite have higher sodium and potassium, and then the illite or the chlorite has a very high magnesium content. Those tend to have much lower firing temperatures. And you know, we see some materials. There's one of Boral's plants in either Tulsa or Oklahoma City. I think they're firing 1600 F. I mean, it's really low, and they get a decent amount of vitrification, but it's actually got a very high potassium content, highest that we normally see. So, you know, there are those things out there, and whenever it comes down to the point where we have to reduce CO2 emissions, if that ever comes along, we're going to be trying to find cheap sources of these guys to make it happen, to bring the firing temperature down. We know what to do, we just have to have a reason to do it. So our materials are made up of a couple of things. So usually if we break down the mineralogy, the main thing we're going to see is the main mineral we're going to see usually is quartz, okay? And we'll talk about why quartz is important as we go along. Behind that, there's usually a clay mineral, okay? So there's some amount of a clay mineral. A lot of cases there's some mica type material, which is sort of a parent of the clay mineral. So, you know, it's not unusual, and typically it carries some fluxes with it, so it can help you with firing temperature. The other things that we're interested in are, you know, any minerals that contain calcium or sulfur, and we'll talk about those in detail. Carbon or iron minerals. Sometimes you get stuff that has iron and may pop. I don't think that's me. I thought I silenced. Yep, I'm on silence. Okay. So, yeah, we've talked about fluxes. If you go too crazy on fluxes, you can get in sticking, you know, where the brick don't want to come apart. Excessive shrinkage, distortion, depending on what form that sodium is, because sometimes we'll try to add a salt to help get better water absorption, and that can, because it's usually soluble, can result in scumming. So we'll skip over some of that, but that's some of the other stuff we look for. So fluxes, typically, you know, like I said, we can reduce our firing temperature. If we need to get a lower absorption, we're not meeting our CB ratio or our cold water absorption, and you can't get more temperature in a kiln. I've been working on for a company way up in the northeast. They're trying to make almost all kaolin molded brick, and the absorptions are through the roof, so they'll never survive the winter there. They can't go higher in their kiln. It's limited on temperature, so we're trying to add fluxes to bring the absorptions down without causing any other problems. And you know, we've gone from cold waters above 15 at the same temperature with just a little bit of some sodium additions down to below 8. Okay, it's still, for that climate, I'd like to see it even lower, but you know, you can do those kind of things. You can sometimes you can get some odd colors out of these additives. They will intensify, you know, sometimes the iron or the manganese. This typically, as the water absorption goes down, everything becomes darker, and you can get more benefit out of that. And sometimes we're using them to try to either tie up soluble salts, and we'll talk more about scumming and efflorescence, or we're trying to plug up the pores at a lower temperature so that we eliminate some of especially efflorescence. So I'm going to skip over that. That's kind of redundant. This is what we call a phase diagram. And I was trying to show here what happens. So if we take silica by itself, to get glass or liquid formation, we got to get it up to 1723 Celsius, really hot, to melt sand. When we start adding sodium to it, you can now start to see your first liquid in the 800 degrees Celsius range. Okay, so just an idea of how powerful fluxes can be. We won't go into how to read that. I had to spend a whole semester on that, and I hated those things. But this tells you if everything was in equilibrium, which we rarely are because of that time temperature dependency, what we could expect for certain compounds. There are whole books of these that you can go look up. This happens to be one for sodium, alumina, and silica. Again, this would be a little more realistic of our materials. But if I had, if we were looking at our blend of raw materials, so we said it's roughly 65-70% silica, alumina being the next biggest thing. Our firing temperature is somewhere in here, so in excess of 1600. We add some sodium, and that starts, and this is all in Celsius. Usually you're looking for the lowest. These are called either eutectics or paratectics. We won't go into that. You can see these same kind of diagrams when you're looking at solders. Okay, they use this same kind of idea when they're blending a solder so it melts at a low temperature. You can start to see liquid as low as 700 degrees Celsius. Okay, so just an idea of how fluxes work. One of the tools we use a lot is a screening tool. This is called a gradient furnace. Do you have a gradient furnace? Okay. So you can either use it for color development, or you can use it to see, some people will do a bar and they'll fire the bar, and the way it works is the winding is real tight at the back. It's a resistance furnace. And then the spacing between the winding spreads out as you come forward, so you get the hottest temperature in the back, and it's set up so that you get a steady decrease. And I think we get about 250 Fahrenheit range on ours, from the hottest to the coldest. Mike's got a way of recording the temperatures now, but if you do these little pellets and you make sure you line them up under the thermocouples, you can go do water absorption on them and see how water absorption and color are influenced as a function of the firing temperature that the piece sees. So that's a good...
Have you guys seen your gradient bars? Y'all have.
Yeah.
That's what they were made.
Okay.
Gradient bars.
Yeah.
Most of the guys have seen a gradient bar.
Yeah. So that's a really good tool. We don't use nearly as much. And if you go this pellet route, you can get a little extra information than just color and appearance. The other thing we do occasionally, we've got a little colorimeter. They make them now that actually will talk to your phone. They're Bluetooth, and they're pretty cheap. So it looks like a pack of Lifesavers. And they're pretty accurate, and we use that and get a color reading off these too. So you can get color as a function of temperature. So that's a common tool, and this was a study. We were worried when some of the environmental regulations were coming on. We were real worried about there was going to be a cap on CO2 emissions. So this was probably about 8 years ago. We were working on this, and we were trying to come up with quick, cheap ways we could drop firing temperature pretty dramatically. And so what I've done here is I've made a series of bodies using phosphates. Okay. These are potassium tripolyphosphates. Sodium tripolyphosphate is in a lot of detergents. It's just a good surfactant, and it helps to either be a deflocculant, or because of that sodium and the potassium, it acts like a flux. So we added some pretty extreme amounts. This is our material with nothing, going from 1700 to 2025, and that would be the blue line. We're looking at our absorptions. So we actually increased our absorption some where we bloated, but we were trying to stay below 8%. And then as we added more and more of the phosphate, we were able to get lower absorptions, but we didn't get a big reduction in temperature with that particular experiment like we were expecting. And we also kind of played havoc with our colors. So anything beyond this 5%, it started to go kind of brown on us. Another tool you can use, this is called a dilettometer. Okay, you've got a dilettometer here, I believe. And basically what that does is you have a little piece of your material and you fire it and you monitor the dimensional change as you fire it. Okay, so when it goes through the quartz inversion, which we haven't still talked about, the material tends to grow a little bit. And so that's right in the range of the quartz inversion and the clay mineral decomposing. Then you get out here and that clay relic we talked about after we decomposed it starts to make something called mullite. Okay, you typically see that in this range. And then we have the glass formation. So what we've done is we've taken, this is basically calcined sewage sludge that was, I can't remember what city was trying to get rid of it, but it's got a lot of potassium in it. So it's actually, if somebody will give it to you, it's a good flux. And we were trying to see how much it would lower firing temperature. So, you know, if we're looking, say, here at 1% shrinkage is a baseline, we're close to 2,000 for the reference, and then we drop back closer to 1,900 as we increase that amount of city ash to get the same amount of shrinkage. So it's one of the additives we'd have to look at later on for recycled material and for lowering firing temperature if we needed to. So silica, this one, we've already talked a little bit about it. The chemical analysis I showed you showed SiO2, and that's just how we report it by convention. Unfortunately, that causes a lot of confusion because what we're really interested in most of the time is how much of it is actually quartz, okay? Because that silica goes into there's silica and clay, you know, as part of that clay mineral. There's silica in mica materials, a lot of the accessories we may see, and but we're interested in what's purely quartz. And quartz does some strange things that other materials don't. It goes through what we call an inversion. Okay, so Mike will talk to you some more about this because this does cause a lot of problems. So this is another form. Remember I showed you a weird looking phase diagram earlier? This is another phase diagram. It happens to be not true for the most part, because what they say is I take quartz like beach sand and I heat it up. This is true. Get to about 1066, and for whatever reason it decides it doesn't like the arrangement of atoms anymore, and it will spontaneously change and it grows. Okay, so the quartz mineral gets bigger at that temperature, and this is not something that's kinetically controlled like everything else we talked about. I can go up and come down and up and down and up and down, and it will keep going through that inversion. Now, the theory says you then go to something called tridymite. Tridymite doesn't actually exist. And then if I kept heating, I would take that tridymite and I'd go to cristobalite. And I'm good anytime you are. Okay. You do see cristobalite in kill cars. What happened, the guy who was making this phase diagram, everything was taking too long. So he put something called sodium tungstenate in it to make it go faster. And there's been a lot of papers on this. Tridymite only exists when you have a lot of sodium or potassium. It's not really a silica phase, it's an alkali silicate. Okay. The only time I've ever seen it in a brick are some old brick that came out of Fort Sumter in Charleston Harbor. So I don't know if there was salt in the clay when they made it, and that made the tridymite, or it converted over time because that's a pretty severe exposure there. But that's the only time I've ever seen tridymite. It's not really a quartz phase. So what happens is on heating, I get to about 1066, and I go from this low quartz to the high quartz. And generally in brick, this is all we see. We don't get hot enough to go to cristobalite. When I cool it off, it goes the other way. Okay? So I've seen brick with very low compressive strength. And you start looking at the cooling zone, and because of the way the fans are positioned, they go through this several times in the cooling zone. And you're doing damage every time you go through that inversion on cooling. You just can't help it because of that conversion. I'll show you some pictures later, but you can always pick out the quartz grains in the clay if you look at it under a microscope, because they're shattered. They tear themselves apart. And if your quartz is big, there's a lot of the quartz, or you're going through that change too fast, you do damage to the brick. Okay, so that's something to always consider when you're dealing with that. So with deck block, they keep firing, and they'll fire it hot enough that some of that quartz converts to cristobalite, and it stays there. This is a inversion. And then when it goes to a new formula or a new compound, it's called a conversion. And then sometimes around the lab, we'll use something called fused silica. We use it for a lot of labware because it has a very low thermal expansion. It's basically just pure quartz glass. It's kind of expensive because you got to get it to a high temperature. But you use it for certain purposes around the lab. So the ones you really see are the alpha to beta quartz, and then in your deck block, this has a low temperature inversion, but this happens to be about the point where the block come out of the kiln. If there's a lot of cristobalite, that can be a cause of early deterioration in your kiln car deck block. So we see that from time to time. So this is a dilatometer curve for a very high quartz material. It looks kind of funny, but what you're seeing here is, everything has expansion. So when you're building a wall, typically you're going to put in an expansion joint, right? Just from normal heating up during the day. Everything does that. So your brick on the car, as you're heating them in the kiln, are growing just because of thermal expansion. So we see thermal expansion up to a point where probably the clay mineral's decomposing, and then we go alpha to beta quartz, okay? And you get a big jump. And then we come out and we start to make some glass, but in a high quartz material, typically you don't make a lot of glass because they tend to be a little harder to fire. And then you start cooling off, and this is where damage, some people call damage from the quartz inversion dunting. Have any of you ever heard that term? Okay, that's what causes dunting right here. On the heat up, we're not so much worried about it because we haven't made the glass yet. The body's a little more forgiving and it can tolerate that expansion. Okay. By the time, theoretically, we get back to here on cooling, we've made glass. The glass is stuck to that big quartz grain, and then all of a sudden the quartz grain is going to try to pull away from the glass. And because it's stuck to it, it can't really move as much. And depending on the magnitude, you can do damage. Now, this is a material from North Carolina, so it's nobody's in the room. And they successfully make brick out of really high quartz stuff. But you got to be very careful and design the cooling curve properly for that. But that's one way to look at it. I'm actually going to spend a little time talking about quartz. If any of you are coming on Thursday to the Structural Clay Products meeting, Mike's going to talk about rheology, and I'm going to talk about quartz. So this is, if you could look at, under a microscope, look at your brick. This has been polished, so everything's nice and flat, and it's easy to see. It's real easy to pick out the quartz grains. There's always sort of a halo around it where it's tried to pull away, and they're usually all cracked all to hell, just like in here. Okay, so that is the way you look for quartz grains. Now, one of the things you're listening, I don't know if any of you still do this. Do you ring brick together? Listen to the sound? Okay. So the glassy phase that's gluing everything together, a lot of glass gives you a nice ring. Okay. The more of this kind of stuff you have, the duller it gets. Okay. Because you're starting to damage the glass, and you just don't have as much strength. So if you've got a dull or dead brick, it's probably because something went wrong going through quartz. Either there's too much quartz, or you went through the inversion multiple times in cooling, or something like that. So that's just a close-up of one of the grains, but quartz is pretty easy to pick out. These are pores that are left behind. May be open, may not be. But remember, we had a lot of little platy material, a lot of little platy particles, and you can, if you think about it, like right here, you can kind of see a plate that's kind of fused together with the stuff around it. So I'm not a microscopist. My predecessor, Dr. Brosnan, was really into this. I think this is actually one of his pictures. But he could tell you a lot more about what you're seeing here than I do. That is some kind of iron-bearing mineral. Usually that shows up nice and bright. So cooling cracks, Mike will talk to you some more about that, but you expect to have a dull ring, okay, because of the damage you've done. Very smooth fracture. Sometimes it's real glassy or shiny looking. They're kind of easy to pick out. So I think Mike's got that picture too, but this is one from Jim Frederick showing a cooling crack and what it looks like. So calcium salts, see where I am. So the most common calcium salt you have in your raw material is probably this calcium carbonate limestone. There's also dolomitic limestone or dolomite. All that means is some of the calcium is replaced by magnesium, but they do the same thing, okay? So you've got calcium carbonate in the body, and sometimes you have calcium sulfate gypsum. Harlan took me to a pit somewhere around here, and I got out and I thought, damn, there's a lot of glass on the ground. And then I realized, do you know where I'm talking about?
I'm not sure.
Okay, there's big, huge pieces of gypsum just sitting on the surface of the ground, but it looks like glass. You do, I think Oklahoma, there's a lot of gypsum in places. I'm not a geologist by background, so. So we can do a couple of things. The LOI, like we said, can give us some indication if it's there. LICO, just like what you have. There are ways to figure out what's organic carbon and what's carbon from carbonates, okay? Because this calcium carbonate is going to decompose in the latter part of your preheat going into your soak zone, and then calcium sulfate will start to decompose toward the end of your soak zone. It's pretty sluggish and hard to get rid of. If you leave the calcium sulfate behind, there's a good risk for efflorescence. That's the most common source of efflorescence. So there are different ways we can look for this. I've talked about it a good bit, but so they can the calcium can act as a flux. It can lower firing temperature. Sometimes it can do weird things with that, and it can make some unique colors. So calcium tends to bleach things. So you go more toward a yellow if the calcium gets really high. I tried to, when I worked for Dow Tile, we wanted to make porcelain. It's right before porcelain tile became, the most common. If you go to Home Depot now, most of the stuff you're going to see is porcelain. And we owned a talc mine in Van Horn, Texas. Okay, so West Texas. And we wanted to use that material to make a porcelain. Well, it worked great if I wanted to make brown, okay, because I could make a beautiful low, almost zero water absorption, low shrinkage, which most porcelains have a very high shrinkage. But if I put any stain in it, because you try to color the body usually with those, if I put in blue stain, I got brown. If I put in green stain, I got brown. And it had to do with all the magnesium coming out of the talc. But I could make earth tones, but that was about it. So they're materials that naturally contain very high lime in, I would say, around the Toronto area, and we have several members in that area. So in the northern part of the country, going into Canada, there's a big deposit of something they call the Queensland Shale, and it has a lot of naturally occurring limestone. A lot of their brick have a yellowish kind of color to them because of this. But what happens with this material, so we're heating up, this would be the clay mineral decomposing, and then we see the limestone decompose, so you see a shrinkage. And then depending on how much limestone's there and how quickly you're firing, you can make a tremendous amount of liquid in a very short temperature range. So what they normally do is they get up to the point where this almost happens, and they build in a soak, and they let some other reactions take place, and you don't get a puddle. But it is, if you have a very high lime content like they do, and they're probably 15-20% calcium in that material, you've got to be extremely careful, because you can make a puddle instead of making a brick because of that reaction that takes place. So something you have to be aware of with limestone. Generally, if it's just a few pieces causing a pop, you're nowhere near that limit. So this is a lime pop. Okay, they typically happen after the brick has left your yard, and unfortunately, most of the time they're noticed they're already in a wall. Okay, so what that was is that was a limestone grain that made it through the process, ended up near the surface of the brick. And so I start out with calcium carbonate, and when I heat it up, I get calcium oxide plus carbon dioxide. Okay, calcium oxide doesn't like to be calcium oxide. Okay, it will pick up any moisture it can, and it will form calcium hydroxide, and it expands, and that's what makes it pop. Okay, so the general rule of thumb with that is you got to get it finer than a certain mesh. Dr. Robinson used to say if you can grind it faster or finer than 30 mesh, you'll never see a lime pop, but nobody grinds that fine. One of the ways you can tell if you think you've got limestone in your material, a really easy way to do it is go to the hardware store and get some muriatic acid, which I'm surprised they let people buy it because it's just hydrochloric acid. Okay, so it's dangerous stuff. You want to read the label and follow the instructions. But if you drip it on your raw material, a lot of people use an eyedropper, and you see any fizzing, there's calcium carbonate there. When you are cleaning brickwork after you lay the brick, most of those cleaners have some sort of some hydrochloric acid, and basically it's doing the same thing it does in the raw material. It's forming calcium chloride and getting rid of carbon dioxide, but it will break down the mortar and let you wash it off the brick without damaging the brick if it's done right. We get a lot of cleaning complaints too, where it's not done right. So always want to be very careful if you're dealing with acids like that. But that's what causes lime pops. So ways to avoid, one of the easy ways is you can look at your raw material, that acid test we talked about, but again, be careful with muriatic acid because it is pretty dangerous. Loss on ignition can be a clue like we've talked about, chemical analysis like we've talked about, and then that LECO, looking at how that carbon number changes. If you have a pure limestone, it's going to come up on the LECO at about 12% carbon. Okay, usually for us, I don't know what you use as a red flag, but anything above 1% we start to get concerned about when we're doing analysis. But 12% is pure calcium carbonate. And then that equates to a 44% weight loss if you're heating it in the limestone. So you can see that. But Dr. Robinson used to say is finer grinding is the way to go. Usually that's not possible, so trying to avoid the limestone if possible. And that once it happens, it's happened. It's not going to keep happening. It's just a cosmetic defect. It's no way structural. People get upset about it when they see it in their wall thinking everything's going to come down on their head, but that's not going to happen. It just, the pieces near the surface will pop, and once it's done, it's done. If possible, stain it, but it's not going to cause any long-term problem.
Riley Essence, Texas Clay, Malakoff.
Jason Hatt, Texas Clay.
Paul from Oklahoma. Mario from Oklahoma City plant. Charlie Brown, Denver plant.
Brian Catterton, Denver plant.
Joe Householder, Fort Smith plant.
George Allen, Fort Smith plant.
Michael Munner, Tampa Lee plant. Brady Cassidy, Kim Rucker, Washington plant.
Drew Simpson, Washington plant.
J.D. Lee, Washington plant.
David Brooks. Perlo Westgate.
They Perlo
I thought they were at Westgate line.
Jim Webb, Pearl.
David Salt, Perlo plant.
I'm from Elkin.
DJ from Bennett.
Danny Burns from Bennett.
Little Bill from Bennett.
Okay, good. Thank you, guys.
Continue.
Okay.
We'll get started again, guys.
All right. So we run into minerals that contain sulfides, tend to cause problems in the preheat. Sulfides would be like pyrite or marcasite, like we talked about, that's more common in some of the East Texas clays. Both the marcasite and the pyrite have the same chemical formula. They just have a different appearance. One's fool's gold. One looks like little black tree roots. The sulfates are also common. This is gypsum. Gypsum is the most common of these salts, although we see all of them typically we're concerned with sulfates when we're dealing with either scumming or efflorescence. So scumming is a salt deposit that may happen in the dryer, and it's usually easy to tell because there are patterns. You can see where the brick were sitting and the air was hitting the brick. Wherever the brick is drying the most, it tends to bring the most salts to the surface, and you end up with that deposit. Efflorescence happens after it gets out, and usually, sometimes you see it in the cube, sometimes you see it in the wall. These salts can actually also come from the mortar. Okay, mortar has a lot of gypsum in it to give it early set strength, so not all efflorescence is due to the brick. And because of that, we've done a lot of work trying to come up with a test, and we have a soluble salt test where there's usually a tracer, and we can figure out where the efflorescence came from, whether it came from the brick or whether it came from the mortar. And 9 times out of 10, or let's say 9.9 times out of 10, it's coming from the mortar if it's from a job, and we can pretty definitively show that. But what we can do with that is we basically we use something called an ion chromatograph. So like if you're traveling here and you stop and you buy like a Dasani water or an Aquafina water, they always taste the same, right? No matter where you buy them. If you flew here from Denver, you bought one in Denver before you left, you buy one here, it tastes the same. They take tap water and they deionize it, so they take out all the salts. And then they use these ion chromatographs to add salts back to give it the flavor that you're used to. So they have a salt recipe, if you will. We use the same sort of tools, and we can pick apart efflorescence and figure out what it looks like. So I've gotten to the point looking at these things where if you see like a heavy white sheen on the brick, it's usually a calcium sulfate. That's the most common. But sometimes you see like a crusty deposit on the corners of the edges of the brick. Those tend to be sodium or potassium sulfate because they're more soluble and they stay in the water for longer. And you end up seeing those at the edges where the most drying's taking place. So you can tell what you're seeing by the type of salt. But there are different ways to look at it, but most of what we do now is a soluble sulfate test, and it can give us a good idea based on the number of whether there's a potential for either efflorescence or scumming.
The sulfides you see in the preheat.
Yeah.
Sulfates you see.
Well, sulfides are real complicated. Give me one more minute and I'm going to explain that. But sulfates, like the gypsum, are pretty common. You can make sulfides become sulfates if you don't give them enough oxygen in the preheat, and I'll talk about that next. But you can use this soluble salt test. It's similar to any of you use barium carbonate? Okay, you're using barium carbonate because you have soluble sulfates in your raw material that would normally cause scumming, and you're adding the barium to try to make the soluble salt into an insoluble salt that doesn't move around with water. Okay, so to figure out how much barium you need to know how much sulfate you got, and we can do that with the soluble salt test. The barium people also they do a Baridex test. It's similar, it's just a little different than what we do, but it's all to the same point. So we can use that also to calculate in the raw material how much barium carbonate you need. So if sulfur is a problem in the fired brick, your best bet is to get it out, if at all possible. The only way to get it out is higher temperature and longer time at high temperature, which also tends to reduce water absorption. So since these things are soluble, you're helping yourself in 2 ways there. One, you're lowering the sulfate content, and 2, you're making it harder for water to get in and find that soluble salt and bring it back out. Okay, so it's sort of a combined thing. But when we first got into looking at controlling fluorine emissions, the big idea everybody had is, we'll just add a little bit of fine limestone to the body and we'll capture the calcium fluoride and reduce our emissions. Works great. unless you got sulfur. Because the next thing that happened is all those bricks started efflorescing like crazy. So again, one of those things where what helps you in one place hurts you somewhere else. So these are some pictures of pyrite. I don't have any pictures of marcasite. I should try to get one someday. I wish I had a little mineral collection, but I don't. But so theoretically, you're going to oxidize this thing to iron oxide, Fe2O3, and sulfur dioxide. But that doesn't always happen. Sometimes you get a partial oxidation, and you'll actually make an iron sulfate, okay, that can react to make other types of sulfates in the kiln. It's not uncommon. I'm dealing with a situation now where it appears that the soluble sulfate content is increasing going through the kiln. Okay, so when we measure the soluble sulfate of the raw material, it's got pyrite. This isn't very soluble, so we're not getting a very good solubility number. The fired brick effloresces like crazy. So we're trying to figure out why. The total sulfur number doesn't really change going through the kiln. So what's in the raw material starts out as an insoluble form, so barium doesn't really help. And then by the time we get it through the kiln, we're not really oxidizing it, and it becomes a sulfate that then causes efflorescence. So kind of interesting when you look at it. And that's where we actually have to combine like the LECO total sulfur measurements and the soluble salt measurements. But we do lots of these soluble salts. We do them on fired brick for efflorescence complaints, and we do raw material analysis. So we've already talked about most of this. I'm not going to belabor the point. Just remember, scumming takes place before firing, typically in the dryer. There's usually a pattern to it. You can, if you're setting on like the Sealy plant, you used to be able to see where they sat on the trays. You could see where there were holes, and where the air was hitting the brick, and you get salts right in that hole. If you've got brick stacked, wherever air can pass through, typically you'll see the salt deposit. Wherever the brick's covered, you don't see the salt deposit. Bad thing about scumming is, though, after you fired it, that becomes a permanent surface feature. Okay, it's incorporated into the surface, and scum doesn't come off after it's fired. It's generally permanent at that point. Efflorescence, you can have some luck with cleaning, depending on what it is. But it's we still do a lot of work on scumming and efflorescence. These are the ion chromatographs. Like I said, we can measure different salts. We also use them for measuring fluorine and chlorine emissions. So we do a lot of things with them. And then we can also do total carbon and sulfur. We have a LECO just like the one here in the lab. So you can get a total sulfur content on a material. Sometimes we heat it up, and we can try to differentiate what's from pyrite and what's from sulfates. This is something a long time ago. There used to be a guy here, Mike Vickers. He's the one who pushed me to go after this, because he was trying to measure siderite in raw materials. And siderite's not easy to measure. Siderite's an iron carbonate that can cause a lime pop. But he's responsible for me going after this kind of stuff. Here's some examples of scumming. Again, that's pretty permanent after it's done. And here they were trying to use barium carbonate to eliminate it. So that's no barium carbonate, 0.2%, 0.4, starting to get it under control. A lot of times you see these stripes where the brick on top was sitting there. You always look for scumming. You can see a pattern. Yes, sir.
You have cars coming out of the dryers with the scumming. Is there any way to correct that, or run it back to
wash it off, I guess. I've never tried to take scumming off a car. Usually we only see it after it's come out of the kiln.
Okay. But you said that it occurs before you go into the kiln.
Yeah.
So
it's basically those salts are moving around in the dryer. So as you're drawing the brick, the salts are going with it to the surface. So either you've got to what most people do in that case is they add barium carbonate to make the salt insoluble so it doesn't move.
those cars are basically unusable.
Right.
Right.
Yeah.
I don't think you can get them off.
Right.
Yeah.
You see it there.
All right. So efflorescence has a cycle. The salespeople and the people that deal with complaints talk about this a lot. We've already talked about it a little bit, but the brick get wet, there's soluble salts present, and a lot of these cases, we're looking at mortar or concrete or other cementitious materials that the brick's in contact with. They have an unbelievable amount of soluble salts that can end up in the brick and on the surface. And with that tool I just showed you, we can figure out where they came from. So usually there's some sort of tracer we can use, but the customers and the salespeople deal with quite a bit. Unfortunately, not that much of it is due to us. A lot of it's just due to the fact that we have the darker product next to a material that's high in soluble salt, and it tends to end up on our product. But we have tools to help with that. So carbon can come in a lot of forms. Everything has some organic carbon. Our materials are materials that have been weathered and typically transported by water to the point where we mine them. And along the way they pick up all kinds of contamination. Could be dead leaves, dead animal, whatever. And it leaves some organic material in there that has to burn out. That's usually in the early preheat. And you know, if you don't get that out, it can lead to coring or things like that, or bloating. And I used to work on Bennett's material. It was real easy for that material to bloat because it actually had limestone. And the temperature limestone decomposes varies by how much carbon dioxide there is in the kill atmosphere. And so if the kill was running sort of reducing, the temperature for the decomposition got higher and higher while the glass formation temperature is going lower and lower. And if you got them too far out of sync, you sealed the surface and all that carbon was trapped. So that's a pretty neat example of bloating there. And then you can have inorganic types of carbon, carbonates. Remember I told you dolomitic is just mixed magnesium and calcium carbonate. Siderite, which is the one I was working on with Mike Vickers a long time ago. And how do we identify it? Most of the time we're going to the LECO with that. You can have heat in the body. Sometimes we've looked at fuel savings over time, and we've looked at what you can do to make the body heat itself. So we had one of the kill manufacturers come in our lab, and actually they modified one of our shuttle kills to the point where it basically got the brick up to a certain temperature, and there was enough carbon that then it started, instead of metering gas like we do to keep the temperature rise going, it metered air to control the combustion rate. And the brick would fire themselves after we got basically you had to get the fire started in the brick. They weren't beautiful, but basically you could fire the brick and it made enough excess heat that you could actually generate some electricity on the side if you wanted to. So you could make something, it wouldn't be a face brick, it would have to be maybe a backup brick or something like that, but they were generating enough excess heat to fire the brick and to have some left over. Problem is you got to be careful of bloating in hearts. We'll talk more about that later. So when we're burning carbon, what has to happen? We have to think about, if we think we've got a core, what happens is over time that core is getting smaller and smaller. Mike's going to talk a lot more about coring tomorrow. But you've got two things going on. You've got to have oxygen going into the brick, and then you have to find the carbon and burn it, and then the products of combustion have to come back out. And there are times, I'll show you some thermal analysis when we get to firing, but there are times like when the clay mineral decomposes. There's enough gas pressure from the water trying to leave that's generated from the clay mineral that all combustion stops. You don't see any carbon burnout during that period. So a lot of things go on to remove the carbon, and there are tricks you can play. One of the things we did with red body floor tile, in the tile industry, you're firing cold to cold in about 45 minutes. Okay, it's like a pizza oven, those roller hearths, and you don't have time to mess around with a black core. So we would add a little bit of manganese, MnO2, which gives off oxygen itself, and it would give oxygen in the body to help burn out that carbon. So there are tricks you can play on that. So some typical carbon contents, you know, we kind of watch these. We can see the sulfur. So these come off of a LECO, like what you have here, and then you can do the soluble number. These are percent. That's part per million. So basically, you divide that by 10,000 to make it a percent. So these are small numbers. But these are very typical numbers. But you know, when you start seeing numbers like this, as a general rule of thumb, working with soluble salts a lot, anytime this number gets to be over 100, there's a good chance you're going to have some efflorescence in the brick or scumming in the dry brick. So it's a fairly low threshold of what can cause it. You know, you use these as process control or quality control if you can watch the raw material. So you watch the particle size, make sure it's staying relatively constant, and then you want to watch some, you know, depending on what's going on. We don't measure everything for everybody. We've got a place in Oklahoma, all we do for them is crystalline silica and carbon, because they either are having dunting or bloating, depending on which extreme they're on. And hit the wrong button. We try to keep them, well, that's good, we're done with that one. We try to keep them between the hedges where the carbon and the quartz work. So it just depends on the raw material. There's certain things you look at for every plant. Any questions on raw materials? That was a quick introduction. So there's stuff in our magazine. The old issues are on our website. They're webinars you can go watch. They're MP4 files, so you can watch them on your iPad. And then there's that WikiBrick that's available.
And you guys, the webinars are really good. Everything he's talked about is in those webinars too. So, I mean, you know, he covered a lot of material. And if you could absorb and understand everything he just said, man, you know a lot about making a brick, okay? So these webinars go through the same thing.
Yeah.
And there's quite a few of them that touch on this, about mixes and particle size and all kinds of stuff.
Yeah.
So it is available if you need to know how to get there.
So if you're you go on and you request a password, and Caroline, who works with us, will approve you. If you're using your home email or something, just make sure you say I work for Acme Brick, and that's how she'll know it's okay. So now drying. Drying is a very difficult subject. And I'll be honest, there's a lot of hand waving when you talk about drying. Okay, so drying, a lot of ceramics is art. Okay, it's not as much science as we'd like. This is a real arty part. Okay, so we talk about things in very general terms, and some of it's hard to measure. And that's something I've got a webinar scheduled for later this year, and I haven't had time to do any work on it yet. But I want to try to come up with we talk in drying about permeability of the body, open the body up, make it easier to dry. But we don't have any way to put a number on how permeable the body is. So I want to come up with a quick test for that. Do y'all do anything for that? I'd like to be able to compare and say, okay, this looks like it'll dry better than this, without doing a drying test. And so I think that would help us a lot in this understanding. So that's something I'm working on. The good thing about being around a university is you get a lot of students in the summer that forget to make plans, and they need money to pay rent, and they come looking for jobs, and the university sets a scale, so we don't have to pay them very much, and we get some help, and hopefully they learn something. So when we're talking about drying, there are two things we have to consider. We've got to consider the conditions that drive the drying, okay? That would be the temperature and the humidity and the airflow in the dryer, okay? Because those are the variables we have to influence the drying. And then, like I was just talking about permeability, we've got the body, or the characteristics of the body that tell us how easy it is to move the water through the body, okay? And that also, some of that has to do with the setting pattern, the coring pattern. A highly cored brick is easier to dry than a solid, okay? Because basically the longest distance the water has to travel is reduced in a cored brick versus a solid. You know, you got to move water further. So looking at moisture movement, there are different types of water, and they do different things in the brick. So Dr. Brosnan made this, my predecessor, and I would have left this one out. I never remember to take it out. he's talking here about the water that's part of the clay mineral, okay? And once it's removed in the preheat, it's gone. But when we're talking about drying, we're really interested in these waters. So actually, I'm going to skip to the next slide because I've never liked that order. So when we start drying a brick, the first water we're going to remove is the forming water. Okay, what is the forming water? The forming water, when we add moisture to the raw material, we're trying to get a film, basically, a lubricating film between the particles that allows them to flow over each other. So the more water there is, the more theoretically separation there is between the particles. Okay? The more shrinkage we see. So we can, to some extent, control our shrinkage by controlling or being consistent with the amount of water we're feeding in the material. Now, some of you, I know you've got too much just coming out of the ground, and you don't have a whole lot of control over that. But the forming water comes out first, and that's the water that's most critical for us. That's the water that's related to shrinkage. Okay? So usually at the beginning of your drying cycle, you're trying to limit the rate that you dry. You're trying to go as slow as possible. I know I visited you in Denver 2 years ago maybe, and when you live in Denver, and even when you live here, the humidity's low, okay? Low humidity means you're going to have a high drying rate because water wants to come out of the brick. And you were trying to slow it down. So you had rooms, basically, tents where you were misting the brick. And the whole point is to try to slow down the rate that forming water's coming out so you don't get cracking. Because if you remove it too fast, you make stress and you cause cracks. You know, in the southeast where I come from, we don't have a problem with low humidity. When I first moved to Texas, it was in February, and the humidity was 14%, and I've never been so chapped in my life because I grew up around Charleston, South Carolina, and I don't think we drop below 80% relative humidity very often. So I got a lot of advice on how to deal with chapping once I moved out here. But, you know, it's the same thing. So humidity drives is one of the controlling factors that we're trying to limit to hold on to the water. The next water would be the pore water, and that's the water that's in between particles where we don't have perfect packing. And basically, it's water sitting in holes, okay, where there's nothing there, in voids. And it doesn't really do too much. The third water, and as we go down this list, this is requiring more and more energy. So that first forming water, we're trying to actively slow it down and stop it. As we move, especially into the capillary water, we're starting to have to put in energy to make this happen. So in your drying cycle, in the beginning of the dryer or your holding room, you've got very high humidity, hopefully, and low temperature. And as you move through the dryer, the humidity's coming down and the temperature's going up. So this capillary water is water that's in very small pores, okay? And because of surface tension, those pores want to hold on to that water. Okay, we get into the same thing when we're talking about durability. Those little pores that are left behind like to pick up water. Okay, anybody ever heard of IRA, initial rate of absorption on your brick? Same thing. Okay, same sort of pores we're dealing with there. When I was a kid in school, I remember taking a piece of celery and cutting it in half, and you put it in red Kool-Aid, and you watch it lift the Kool-Aid. That's capillary suction. So the smaller the pores get, the more suction they have because of the surface tension of water. And then remember we talked about the montmorillonite type particles, how they have a lot of surface area. Well, water is a polar molecule. I kind of think of it looking like Mickey Mouse, okay? So you got an oxygen with a negative charge, and you got two hydrogens with a positive charge. So they sort of look like that, but you would assume they're little balls, you know, if you think about chemistry. That water, I've got a clay particle that's got a surface charge, and I've got this water molecule that's also got a surface charge. Well, they like each other, okay? They satisfy each other's charges because nature doesn't like to have unbalanced charge, and they hold on to each other. So this last water, you've got to do a lot of work to get rid of it. So usually you're at a pretty high temperature by the end of your drying cycle, depending on the type of clay mineral you have, trying to get rid of that hygroscopic water. So that is the way that we take water away. And then in the preheat, you would get rid of that crystalline water, but that's part of the clay mineral. I don't really think that is part of the thing here. So here's my Mickey Mouses. I jumped the gun on you. So that hygroscopic water, this is a theoretical depiction of one of those little clay platelets. It's got positive charges on the edges, negative charges on the surface. So these hydrogens like to line up with the negative charge on the surface to fill it up, and then the positives like to go around the edges to satisfy the negative charge on the water. When you add a deflocculant, basically you're just putting a salt layer, an extra charge layer in here, and it helps separate everything. We talked about gypsum earlier. So you took me somewhere around here, and there's gypsum everywhere on the ground. Okay. All right. So I always think of that. I use that as an example. All right, so capillary water, remember that's the one I was talking about in the really small small pores. It's got a fancy looking equation here, but basically all you need to know is that suction goes up is the radius of the pore goes down. So the really small pores are what grab the water and want to hold on to the water. So we have to give it enough energy to break it out of here. So this would be in the later part of the cycle where we're trying to remove that water. When we're dealing with a fired brick, we're talking about pores with diameters of less than 10 microns. Okay, micrometers. Remember we said a clay particle's 2 microns. So we're in that same order of magnitude. Really small pores. But those make up a fair portion of our brick. And that's what can either cause suction in the fired brick, or it's water that we're having to work to remove in the dryer. The pore water, that's just the water in any voids that are in the brick. So you can talk about particle packing with that, but tighter bodies make it harder for the movement of water. A tighter body, and that's what I was talking about earlier. We don't really have a way of measuring these things when we say a tight or an open body, and that's something I want to be able to develop for us, where we have a test where we can differentiate things. But the tightness of that body makes it hard to remove that water. And basically this is talking about water passing through a pipe is an analogy. And basically what it's saying is the ability of that water to move has to do with the pressure difference, okay, for the movement of the water. We're creating that driving force, and you can think of that as a driving force, by the humidity differential between the inside of the brick and the air in the dryer. Okay, so we're manipulating the air in the dryer to cause a driving force. Initially, in the beginning of drying, we want this to be pretty minimal so that we're controlling the drying rate, and as we go further and further in the dryer, we're making that difference bigger, so we're forcing drying. And then the path that the water has to move. Okay, so like I said, a highly cored brick has a shorter path for water movement, so it's easier to get the water out. A solid brick, this would be a bigger number, and it's harder to get the water. So this is an example, if we could think about what's going on in the surface. You've got airflow, and that air has certain characteristics. Now, in the past, we would pull out psychrometric charts to do this, but I use something now. It's just one I found free, and it does everything I want I use a Google phone, so this is on the App Store. I know they're the Google Play Store. I know the Apple App Store has some, but I use one called AirCalc. And on AirCalc, so if I assume, anybody know what the humidity is today? About, 40, 50%? Okay, we'll assume that. So it's 70 degrees, and it's 50% relative humidity. Let's talk about relative humidity for a second. I can see how much energy is available in the air for drying to take place. I can see how much moisture the air contains, the absolute humidity. Remember, relative humidity is relative to temperature. Okay, so if I'm looking at 50% relative humidity and it's 30 degrees outside, that's a moisture content. If I'm looking at 50% relative humidity, it's 80 degrees outside, that's another moisture content. Big difference in how much actual water's in the air, even though it says relative humidity. So typically when you're dealing with drying, we look at something called absolute humidity. Does anybody know what this TW is? Anybody ever measured humidity in a dryer? Okay.
Versus dry bulb.
Yep, that's a wet bulb temperature. Okay. Some people will call this a dry bulb depression. Okay, the difference. The way you used to measure humidity in the old days, before you had solid state sensors that would do it, is you would have something called a sling psychrometer, and I didn't think to bring mine. But basically it's two thermometers side by side. One of them has a little sock over the end that you wet, okay, and you go in the dryer and you swing it around, and if the air is wet, not much evaporation will take place on that sock, and the two temperatures will be almost the same. Okay, it means a high humidity. If you go in and you swing it around and there's a big drop in the wet sock or the wet bulb one, you know you have a low humidity, and you can actually calculate the actual humidity off that. So what this is saying is that's the driving force for air movement. This is a film coefficient, and a film coefficient has to do with how the air interacts with the surface. Okay, do you have air blowing across the surface? How fast is the air moving? Is the air hitting the brick, at 90 degrees, or is it parallel? Basically, it's a way of describing how well the air is exchanging its energy with the brick. So, are we doing a good job of heating up the brick with the air, or is it, not much movement, not very efficient? And then this is the heat of evaporation. So the rate of drying is proportional to the driving force, okay, basically the humidity, the film coefficient, which has to do with the way the air interacts with the surface, and the evaporation rate. So in the past, we'd start pulling out psychrometric charts and we'd start reading points, but now that we have the calculators, I just don't see the point in doing that anymore. Because I can look up the properties of the air. So we'll talk a little bit about calculations we can do in a little while. But theoretically, if I knew the conditions of the dryer and I knew the moisture content of the brick, how many brick per hour I was putting through, I know if the air is capable of removing all that moisture. Okay? So then it becomes how efficiently am I running the dryer to make that happen. If I do that calculation and there's no way, I've got more moisture than I can theoretically evaporate, no matter what I do, the brick are going to come out wet. So you can do that kind of thing with this if you're interested. And we have examples of that on our website. So when we're looking at these stages, remember we talked about the different types of water do different things. There are different stages of drying that correlate to those types of water. So typically we talk about stage 1 is the initial stage of drying, and it's the stage where all the shrinkage happens. And it's pretty stark. You can see this in drying curves. You can also see it there's an easy way to tell where this happens in your brick. I think I've got an example I'll show you. But just by putting a thermocouple on the surface of the brick, you can tell where it transitions out of the shrinkage stage. And I thought I'd discovered something pretty interesting. But any of you ever met Don Dennison? Works for Lingle stuff. I was telling him about it because Lingle provided this big dryer. And he basically told me, no shit, Sherlock. Everybody knows that. So he kind of burst my bubble on that. But so we do this kind of measurement quite a bit, looking at stages of drying for brick. So what's happening is this is that forming water that's separating the particles. And when it is gone, we start to move into the pore water, and then we get into the capillary and the hydroscopic water as we go on. So the way we control this part of drying is different from the way we control this part of drying. Typically here we're trying to have very high humidity, low temperature, and as we move on, low humidity, high temperature to try to speed things up. So just the way we control the drying. You can plot it in different ways, but basically you see a very constant shrinkage rate. in that first stage of drying, and then you see what they call a first declining rate period and a second declining rate period when you get into stage 2. So the forming water and shrinkage takes place, and then you're getting into the pore water and the capillary and the hydroscopic water. This has to do with the film coefficients. We won't really spend a lot of time on that, but basically what happens in this first period of drying, evaporation's taking place at the surface. So you've got a continuously wet brick. So it's capable of moving water to the surface and evaporating. Once shrinkage stops, the evaporation starts to take place below the surface of the brick. And the further you get into the brick, the longer the water's got to travel to get out. Okay, so that's another complication there. So that's where we talk about open body, closed or tight body type of thing. Has to do with how easy it is to get the water out down here. Typically, also when we're controlling, we try to open the body. Usually you're adding a grog or some coarse particles. You're reducing the total amount of shrinkage too, so you make it a little easier to dry. So in stage 1, this is basically my thermocouple trick. The temperature of the surface won't exceed 100 degrees C or 212 Fahrenheit because that's where evaporation's taking place. It's like a tea kettle. Until all the water's gone from the tea kettle, it's not going to get any hotter than that temperature, even though you keep it on the burner and you're applying energy to it. So in stage 1, what we're trying to do is not develop excessive steam pressure in the pores. Okay, so we're pushing brick up to or water up to the surface to evaporate, and if we create too much of a driving force, we create excessive pressure, and you can get steam spalling or explosions. Anybody ever done that where you popped brick in the dryer? No? Okay. I've done it in the lab a few times. It's exciting. So we used to do a test too. I don't know if you ever do this, where you wrap a brick up in foil and you put it in the dryer and you open it up and you see if it falls apart. We used to do that in the short course when Dr. Robinson was alive. Yeah. And we'd have some brick that had very little clay, and it would just turn to sand when you'd open it up. It was amazing. I need to bring that test back. All right. So when you're in those declining rate periods, basically the thickness of this dry skin that you've got to move water through becomes important. And this is starting to get a little too much math in it. But you talk about a shrinking unreacted core model. You can do all kinds of math if you were interested in it. But it basically becomes progressively harder and harder. And this thing is saying the same thing. So we're predominantly using temperature when we get toward the end of the drying cycle to force the water out of the interior and through that shell without causing any damage. So basically the takeaway here is, because shrinkage is taking place in that first part of drying, we've got to dry slowly so that the particles can come together. We don't create excessive pressure in the pores to avoid cracking. We've actually seen in our experimental drying, we can, within a few tenths, based on how fast we dry the brick, we can influence the total shrinkage. So if you dry very fast, this seems counterintuitive, you get a lower shrinkage than if you dry very slow. And the way I've always thought about it is, if I've got two particles coming together, there's a water film between them, and I go very fast, they hit, and they may not be in the most beneficial orientation to each other. Okay, so they just bump into each other real quick. But if I'm drying slow, they can orient, and they can come to a lower stress state where they're happier next to each other, and you end up getting a slightly higher shrinkage. So the particle size distribution is what is very important for controlling shrinkage. So typically we're interested in the coarse end of that size distribution to control that shrinkage. Very fine mixes tend to have a lot of shrinkage, a lot of drying difficulty. Coarse materials, there's some shales in North Carolina that make a pretty brick, but you can basically throw them completely wet in a dryer and it doesn't seem to affect them. because they're sufficiently porous that the water can get out. All right, so this is some stuff we did with that experimental dryer. I won't spend too long on it. Yeah, we're in good shape. So looking at different drying curves. So when you're trying to control drying, you've got a number of variables that you can work with. You got air temperature, obviously you got humidity, the speed of the air, the way the air is interacting with the brick, okay? Is it flowing parallel to the brick? Is it impacting the brick? And some of the new high efficiency, high speed dryers that you can see in Germany, they're trying to get really turbulent mixing of the air and the brick to make sure that you're getting as uniform drying as possible. And they can get faster rates out of that. How open is the setting pattern? How accessible is the brick to the air? The permeability of the raw material, the shape. How do you design the coring? Because coring does come into play when controlling drying. And keeping the forming water to a minimum. Okay? More water you put in, the more water you got to take out. And the more water you put in, the more shrinkage you see. So this is a balancing act. You can't have too little water or you're going to have extrusion problems. But too much water, the brick will be soft and it's harder to dry. So it's always something to consider. But what we were trying to do is figure out how fast we could dry. So we played with basically the temperature, humidity, and airspeed, trying to get different drying rates to see where we saw cracks develop in the brick and where to figure out how fast we could dry. So basically, what we're doing here is increasing the drying speed by manipulating those things. And this is the dryer we've got. If you've been to our lab, you've probably seen it. We can measure shrinkage on brick. We can measure weight loss. This is actually a load cell too, so we could put a whole hack if we wanted to look at designing the layout of the hack to get optimal drying. We could lay out different patterns on there and do drying tests. So you can do all that kind of stuff in there. So this is, remember we talked about, this is just plotted a little differently, but we can see where shrinkage is taking place. So this is increasing shrinkage, and then it kind of levels off on us. So we can see, or excuse me, that's weight loss. This is shrinkage up here. So we can see that's the end of stage 1 right there. So this would be stage 1, and then this would be the stage 2. And this is kind of plotted opposite of what we saw earlier. It's just easier to work with. This is that first declining rate. So this is where we'd be getting into the pore water in the capillary. And then out here we're getting into the hydroscopic water. But this is that forming water we talked about. So you can actually see it on a real brick. So we can go through and we can do different tests, but this is the one I was interested in. If you put a thermocouple on the surface of the brick and you monitor the air temperature while shrinkage is taking place, and that's also where evaporation's at the surface, you see your temperature kind of lagging behind until you get to the point where shrinkage stops, and then it starts to catch up with the air temperature. So that's an old trick to find out in the dryer where shrinkage stops. I didn't know that. I rediscovered it accidentally until Don Dennison told me I was an idiot.
So how close, like, do you need to have your temperature?
All we were doing is basically, it was a fairly thick bead. We were just pushing it in the surface of the green brick.
Okay.
So if you've got a traveling thermocouple, you can see where that's taking place.
What I have is I got a bunch of these, it looks like USB stick.
Yeah.
But, you know, the temperature, humidity data logger.
Yeah.
Right? And so, like, if I had one on top of the brick and one, like, on the frame of the dryer cart.
Yeah.
As it goes through, then you could...
It'd be interesting, too, if you could check different spots on your car.
Oh, I've done that before. And it's just depending on the part of the dryer and the condition of the fans and
Yeah.
a certain area, you can get very wide from
Yeah.
the top of the stack, which is like at, say, 3 stories to the bottom. You have like a 10, 15, 20
Yeah.
degree temperature swing.
No, but that'll exactly, wherever you see that break point, that's where shrinkage is stopped. So what that's telling you is I can now start dropping the humidity and I can pick up the pace on drying.
Okay,
I
so
get-
that could really help me in okay, seeing that line and then where I can hit the throttle.
Yep.
And where I need
Yeah.
to actually, like, okay.
Exactly. That's why I think that's a neat way to do it, because you're not. It's doesn't take a lot to be able to measure that.
So there's just another kind of follow-up question on another one of these slides. On the overview, you talked about air temperature, humidity, and air speed.
Mm-hmm.
So if you're lacking one, or you somehow got a situation due to breakdown or whatever where you don't have air speed or you don't
Mhm.
have one of those, how can you compensate for losing one? What would be a creative way to compensate for that?
If you have no airflow.
Yeah, so like in our situation, like we've got dryer cones, right?
You've got dryer.
Cones.
Oh, okay,
So,
yeah.
As they're cone shaped, so as they come down to a point,
Yeah.
the velocity tries to stay consistent throughout the whole,
Mhm.
height of
Yeah,
the car.
I've worked on a metal corrosion thing with Brian Christensen on that. Yeah.
So we get into a situation where we get in the middle of the dryer and we don't have cones, where
Yeah.
they're either rotted out or whatever, they've fallen over, they fall
Yeah.
apart, and so we get dead spots.
Okay.
And, we might see some face cracking or whatever. But what types of things could I do to help mitigate the effects of that?
That's a tough question. If you got you can balance temperature and humidity to compensate for one or the other. But with no airflow, there's no way to take away the moisture you're drying.
Right.
So,
So I mean, would that mean increasing maybe the exhaust so then you're pulling more out?
well, that would be a way of getting airflow.
Lowering the overall heat into the beginning of the dryer, so then you're not pulling out so much.
I don't know. I've never thought about that. But you can create drying rate in a bunch. There's an infinite number of ways, but based on that. But in your case, yeah, I guess you got to do something to pull the air out.
That's a tough one.
Yeah.
because
We increased our 105 fans and open up cold bleeds
Hmm.
to bleed the hot air off of it, but still have the force of the air to push through the dryers.
Hmm.
That would be a big old experiment. We'd have to
Yeah.
figure out what works best for you.
Yeah, and I mean we don't really have a cold air bleed whatsoever.
We have doors on the sides of ours where we can bleed cold air to control the temperatures in that zone where we don't suffer the airflow, but we do cool down the temperature on it.
I wonder if in those spots where the fans, like the motor and all that is, we could put maybe a T on that supply, and then instead of having it be a 90
Yeah.
straight down from the supply.
We spend the whole day talking about your particular problem. Because part of the problem with that, when you don't have one of those fans, when one of your fans isn't working, and you're still putting some hot air in up at the top, but the fan's not picking it up and driving it down to the floor, then you get hot up at the ceiling.
Oh yeah.
And the floor is not very hot because you're not getting,
Mhm.
you're talking about 20 feet from top to bottom. So
And that's why we get the rolling issues is just from
it's a
that.
tough situation.
Yeah.
I don't know if there's any-
Well, see, I've never operated a big dryer. I can play with lab dryers and measure materials, but I've never done that kind of thing. So we have different expertise when it comes to that.
Keep your fans going.
Yeah, keep your fans going. That's the best advice.
When you jump in there, how many fix those?
I know what you're saying.
Yeah. Yeah, that's when I came back to the center in 2000, one of the first things I did is I came to Elgin, right?
That's sample.
Okay. Well, this was Elgin, when you had that DeBoer plant. The racks, you remember where it would push the racks off? The salt was eating them.
Yeah, eating
Yeah.
everything up.
Yeah, so I came out and met with you all about that, and we did some SEM work on that. So that was 17 years ago.
Yep.
So it's been a while. All right. I lost my spot. Okay. So we were trying to figure out how fast can you go. We were doing this work right before the downturn where everybody was trying to make all the brick they could and trying to get the most out of their kill that they could. So we were trying to figure out what's the maximum drying rate you can push the material to, and then you would take that to the plant and try to achieve that. And I think I've got another slide, but if you talk to Silica, they use a different approach. They use something they call a Bijot curve. where it's basically the same data, but they plot and they're French, so that's why they pronounce it weird. They plot the shrinkage versus the weight loss, and based on their experience, that tells them something about how the material is going to dry. So if you ever deal with Silica, you send Christoph some material, he sends it to us for a drying test. So we do those kind of curves. So the Bijou curve looks something like this, where we've got weight loss and shrinkage. So what he's looking for is what percent of moisture, what's a critical moisture content, where shrinkage is basically getting close to stopping, and then he can speed up. So what we did with ours is we were doing dry modulus of rupture, and we were looking at, so this is increasing drying rate. So we see strength coming along, and then there was a drying rate where we definitely saw a fall off in the strength, and the scatter went up a lot. And presumably it's because we're making cracks inside the brick because we're pushing the water too fast, and it's causing damage to the pores. We tried to also look and see if we could visibly see the cracks, and we had to get to a lot higher drying rate before we could see the cracks, whereas the modulus of rupture picked up that these are the same brick. So somewhere around 0.016% water per minute. We had to get out a lot higher before we could see visible cracks. And then shrinkage, what's interesting, until you get into this cracking period, basically shrinkage drops as we increase drying rate. And that's what we talked about earlier, about the particles approaching each other. So there's a lot of dryer calculations you can do too. There's a lot of drying, new types of dryers that are out there. I saw some weird ones when I went to Ceramitech at the end of last year. But for these to work, you got to understand the properties of the air, and that's that thing, that app I was telling you about. There's an article on our website if you want to figure out how to do these dryer calculations. Dr. Robinson wrote it. It's called "You Gotta Have Heat." Okay, it's kind of a unique name. It'll teach you how to do that's how I learned to do these kind of dryer calculations, but we're not going to go through all that right now. But basically, what you get here is you have your psychrometric chart. So this is a psychrometric chart. This is one of the earlier software packages. And if you can plot your ambient conditions, so what's the air in the plant like, your hot supply temperature, and your exhaust temperature, you can calculate a lot of things here. You can calculate, that's Dr. Robinson, for those of you who haven't ever been on our website. You can calculate how much energy goes into evaporation, how much energy goes evaporating the water in the brick, how much energy goes into heating the air in the dryer, how much energy goes into heating the brick. And we can look at how much total energy is available, how much we're using, how much we're leaving behind, all those kind of things. So this is called a Sankey diagram, and basically I could calculate this if I had some measurements on the dryer. I'm not going to go into all the details, and I could read these properties. This is another example from that "you got to have heat." You can calculate, basically we talk about a sensible energy that goes into a sensible change and energy that goes into a latent change. Sensible is basically a temperature difference. I can feel it, okay? So when I make the brick hotter, I can touch it. That's a sensible change. A latent change is how much energy goes into evaporating water. And if you knew how to read the chart, basically this tells you the absolute humidity, how much water that the air is holding on this axis. And I could read over, and by difference I could calculate how much water was exchanged from the brick to the air. And then in cases where you're not at efficiency, you can figure out basically how much energy is being wasted that could have been used for further evaporation, if you're that interested in breaking it down that precisely. But that's all in that "you got to have heat." You can see how to do that. This would be an example we could have worked through. If we had a little more time, I probably would have sat here and tried to work it out with you, but we're going to pass on that. But basically, there's a solution. So that's the first part of drying.